Okay, there are two methods for doing this that you did a ton in Algebra 1, and we even, those who were in my algebra or in my geometry class last year, we even reviewed it in there too. So this will look really familiar, I think. Okay, one of them is substitution. The other one is linear combination method, or sometimes it's called elimination. Okay, very simple. It's really not hard stuff, but useful. Substitution, remember, that's just where you, in one of the two equations in the system, you solve for a variable, you isolate a variable, and then plug it into the other equation. That's it. Okay? And then you solve for, that eliminates a variable. We'll look at some examples. And then you can figure out what one of the variables is and plug it back and find the other one. Linear combination, in a nutshell, is the one where you try to multiply one or both equations by a number so you can get either the x column or the y column to cancel when you add them up. Remember that? Okay, so we'll look at a couple quick examples of these just to refresh your memory. So with substitution, this one we only use, never use it when it's inconvenient. Only use it when there's a variable that's easy to isolate. So if there's one where it's either the coefficient is 1 or -1, but if there's a number next to the x or the y, you'd never use it ever. Okay, it just makes it too hard. And then you solve for one, substitute it back into the other, get an answer, and then plug that in to get the other answer. It's easier to kind of see an example than it is to go through those steps, though. Here's an example of one we could solve with substitution. Now, what's the variable? There's only one variable here that would be worth isolating. Which one is that?
The y.
The y in the top one is easy to get by itself, isn't it? Right? Because it's got a negative sign, a coefficient of -1. So if I take that first equation and I want to get the y by itself, there's a couple ways to do that. One way is I could just push the 3x to that side and multiply or divide by -1. Tell me if you don't like this better. I think this is better. What I always do, if I've got a negative y on one side, I think it's easier just to add the y to the other side to get the y over there, and then get rid of the 13, subtract 13 back to this side. Does that make sense? To me, that just seems like you don't have to do any multiplying or dividing by negatives. Right? So we would just do that. Push the y over there by adding y to both sides. Subtract 13, and there's my answer. Well, that's not my answer. That's my substitution equation. Okay, I isolated y in the first equation, so now all I have to do is substitute that into the second equation. Now, what I would urge you to do also, when you're doing substitution for any kind of system, linear system, or later on if it's a nonlinear system, whenever you isolate a variable, immediately put a box around it, because you're going to come back to that equation. It's nice to be able to find it quickly, to know where it is. But all we're going to do then, once we isolate the y, we just substitute back up here. And now what used to be a y, we're going to trade for the quantity 3x minus 13, right? The advantage of that being the y's are all gone. Now all I've got are x's in my equation, and so we can just shift into algebra mode and solve for x. What would I do to solve for x there?
Just times 3x and negative 13 by 2.
Okay, good. We'll just distribute the 2 all the way through, right? If I distribute the 2 through, I get that. Just combine like terms. So I'm going to get an 8x, add 26 to this side, right? Give me a positive 16. Divide by 2, or by 8, sorry, and I get x equals 2. Now you know why we had a box around that equation, though, right? Because we'll just go back to the boxed equation. Oh, that's the wrong color. Go back to that boxed equation, and I'm going to take this x value and just plug it right in there. Look, I've already got the y by itself. If I just plug the x in, whatever that simplifies to is my answer for y, right? See how that works? So plug it back in. I get 3 times 2 minus 13 is y, and that's just what, 6 minus 13, so -7. So my answer is the ordered pair, x equals 2, y equals -7. Right? No big deal. No big deal. And then if graphically, what's the significance of that point? It's point of intersection, right? That's where the lines would cross. But we're not graphing it, so we don't see that this time, but that's what it means, right? Questions on that?
No.
Okay? All right, so there's substitution. Now let's look at one where we don't substitute. Okay, I'll skip through this is on this. I gotta double check. This should already be on the website. If it's not, I'll make sure it's there by this evening. In fact, I'll do it this period. So here's an example of one where we would not use substitution. You understand why? If I tried to isolate one of those variables, I'm going to end up having to divide by some number and get a bunch of fractions. And we don't want to do all that work with fractions. We can avoid it. So instead, we'll do the other method, linear combination or elimination. So this is the one where we got to multiply by one equation, or maybe even both in some cases, to make the variables cancel vertically when I add them up. You want to be smart about this now. See if you can pick the easiest way. You always would rather, if possible, I mean, maybe you don't even have to multiply by anything. Maybe they already cancel. Well, in this case, they don't. But if possible, I'd rather just multiply one equation rather than two. Man, do you have an idea? Okay, if I multiply the bottom one by 3, does everybody see why? If I multiply the bottom one by 3, I'm going to get a positive 6y there and a negative 6y above it, and those will cancel, right? Here's how I like to show that. You don't have to do it this way, but I recommend it. I create a new system, and if I don't multiply by anything, I just draw an arrow. It just means leave that one alone. But this one I'm multiplying by 3, so I just put a 3 in the bubble in the middle of the arrow, and that reminds me that I'm distributing a 3 through to both sides. So the top one stays the same, 2x minus 6y equals 19. Now if I distribute a 3 all the way through both sides on the bottom, what do I get?
Negative
9x, okay, good.
Plus 6y equals 30.
Equals 30, good. Okay, and if I add those up, now look what happens. If I add those up, the y's cancel. That's what I wanted. I mean, it doesn't matter which variable I cancel. I just want to cancel one of them, right? In this case, the y's canceled, and so how many x's do I end up with?
7x equals 42.
Okay, now I got one variable in there. It's easy to solve for. Just divide both sides by negative 7. Negative 49 divided by negative 7 is? Negative 7, good. Okay, so there's x. Now, what would I do with that x? Yeah, plug it into, go back to the original system before we made it bigger. Go back to the original system when it's small and easy, and plug x into either one of those equations, whichever one seems to be the easiest. And in this case, there's not really a clear winner. They both seem about the same. But if I plug that x into, let's just say the bottom one. If I plug x in right there, I get negative 3 times, well, that's bad. Negative 3 times negative 7 plus 2y equals 10. Negative 3 times negative 7 is 21. So 21 plus 2y equals 10. What are the two steps in order to get y by itself?
Minus.
Subtract 21. So if I do that, I'm going to get 2y equals 10 minus 21 is negative 11. And then last step?
Divide by 2.
Divide by 2. So I get y equals, and then we know that a negative divided by a positive is a negative fraction. So I get negative 11 halves for y, negative 7 for x. That's my ordered pair. Negative 7, negative 11 halves. Make sense? Okay? That's linear combination. Okay. So we already did all this stuff. I'll skip through this. And there's our answer, right? Okay? Now what happens here? Oops. Which method would be best here?
The second.
Yeah, I mean, okay, yeah, technically they're going to tell you substitution because it's easy to isolate the y. Honestly, I don't care. I almost always use linear combination. Even when I could use substitution, a lot of times I'll just use linear combination. Either way, it doesn't matter. I could just multiply the bottom one through by 3, couldn't I? Right?
But it would cancel everything out.
Ah, okay, look what happens. Yeah, so either way we go, if I substitute and plug in, if I get the y by itself, get y equals 3x plus 5 and substitute that in, or I use linear combination. When all the dust settles here, when I distribute that negative 3, right, to the 3x minus 5, look what happens. 9x minus 9x plus 15 equals 15. Well, the x's all cancel. And I end up with the answer, 15 equals 15. Now, so in the case that the x's go away, and I end up with an answer that is always true, right, that's a true statement, what does that tell us about the solution of this system?
I am.
Infinitely many. Yeah, exactly. And here's how you can remember that. How often is that true? It's always true, meaning it's infinitely true, right? Okay, what does that mean in terms of the two lines that we talked about?
They're the same.
Same line, yeah. The two lines overlap. Perfect. Okay? Same line. Infinite solutions. Infinitely many solutions. Okay, what about this one? This is one where I could use linear combination, right? Multiply bottom by 2. If I multiply the bottom by 2, then that's going to become a negative 6x plus 4y equals 14. If I add those up, look what happens. The x's cancel and the y's cancel, and on the other side I get 14 plus 14 is 28. So this time the x's went away and I got an untrue statement. How often is that true? Never. So there are no solutions, right? What does that mean in terms of the lines? They don't intersect. So what kinds of lines would not intersect in? Parallel. Yeah, exactly. Okay? Parallel. Okay? Make sense? No solution. We good?
Yep.
That was quick, and I would normally do maybe even another example, but I really want to give you a chance to finish that test up. So let's go down to 209.